All right, hello everyone and welcome back. So in today's video, we're going to be covering node analysis. Let's go ahead and jump into it. So goals for today. By the end of today's video, you should be able to know how to write node equations. And while node equations sound kind of scary, you'll see that we're basically just using Kirchoff's current law and Ohm's law. Next, you'll see how these node analysis techniques can be used to solve more complex circuits. Node analysis is an extremely powerful tool that we will be using throughout this class. So please make sure you understand these topics very well. It will build a strong foundation to help you succeed in the rest of the class. Okay, so let's just briefly review what we have covered so far. As I mentioned in our past videos, circuits can get ugly. But the good news is that we can put together a very nice toolbox to help us solve circuit problems. So far in our toolbox, we've already added a number of useful tools. Notice we have our Ohm's law, V equals IR. We've got Kirchhoff's voltage law, Kirchhoff's current law. We also have equations to simplify resistors in series and parallel. And we have those equations for voltage and current division. If you have not already done so, I highly recommend that you keep all of these tools handy. Consider starting an equation sheet and adding to it as we progress through the class. It's incredibly helpful to have all the useful tools in one place as you're working on homework and practice problems. We also talked a little bit about sign conventions. Remember, it's very important to use consistent sign conventions so that you don't accidentally get negative signs or other mistakes in your calculation. Here are the conventions that I recommend you follow. Once again, I call these the bank account conventions. It's not an official term, it's just something I made up. If you learned the opposite of this convention, it's also perfectly okay to use. The important thing is that you stay consistent so that you arrive at the correct answer. So remember, what we do for current for the bank account convention is we use a positive sign if current is entering a node. So if we have current entering, that is money entering our bank account, it is positive. If we have current leaving our node, then we use a minus sign because money is leaving the bank account. You'll remember for voltage, we use a slightly different approach depending on whether we have a voltage gain or a voltage drop. You may recall when we covered voltage sources, if we start from the negative end and walk to the positive end of our voltage source, here we consider that to be a voltage gain. Meanwhile, if I have current entering my resistor and I'm moving across my resistor, I will treat that as a voltage drop across my resistor. So once again, the important thing here is to make sure you stay consistent with the conventions you use. Let's briefly do a quick practice here, and this practice might be similar to something you may see on homework problems. So this practice is asking us, what is the voltage drop across our 3 kilo ohm resistor? and how much voltage must be supplied by the 2 milliamp source. Let's take a moment and think about how we could approach this. Notice we are told that we know what this current I3 kiloohms is. We also know the resistance. So if we know how much current is entering a resistor, and we know the resistor's resistance, is it possible to find that voltage? If you're thinking of using Ohm's law here, that would be correct. Notice the voltage across our 3 kilo ohm resistor is just going to be our current times my resistance, which in this case is 3,000 ohms. Just make sure you multiply both amperes and ohms units so that your final result will be in volts. Second part of this question asks, how much voltage must be supplied by that 2 milliamp source? Well, that might be a little more tricky, right? We don't have a lot of information to work with here, and we don't have a resistance value to use Ohm's law. But what else do we know about voltages? Take a moment and think about it. So, one thing that we do know is that this whole part of my circuit is a closed loop. What do we know about the voltage in a closed loop? Well, if you remember Kirchoff's voltage law says that the algebraic sum of my voltage rises and drops. That sum must be 0. So I can take a walk around my circuit and find out what my voltages are. Let's go ahead and walk clockwise around this circuit. If I walk clockwise around, I can determine that I have some voltage rise from my 2 milliamp source. And then if I keep walking around, I'm going to have a voltage drop from my 3 kilo ohm resistor. Those are the only two components in this circuit, so their sum must be 0. So what does this tell us about the amount of voltage supplied by our 2 milliamp source? Notice, if we rearrange our equation, we can determine that the voltage supplied must equal the voltage dissipated by the 3 kilo ohm resistor. This is the power of Kirchoff's laws. We can use Kirchoff's laws to help us find unknowns in our circuit that might otherwise be fairly difficult to determine. Let's go ahead and try one more practice question here. So here we have a circuit, and we are given that we have a 2 amp current source. We also are given the values of these resistors. So we've got a 6 ohm resistor, we have a 3 ohm resistor, 1 ohm resistor, and a 2 ohm resistor. We are told to use current division to determine the current I1. Why don't you go ahead and pause the video and give this a try. And when you're ready, you can hit play. See if you get the same result as I did. Okay, so let's go ahead and show how we can use current division here. Remember, current division will tell us the current across the nth resistor in parallel. So here, it will only work in circuits where all the resistors are parallel to some current source. And the current division equation tells us that the current across the nth resistor that current is equal to, we have 1 over Rn, where Rn is the resistance of our nth resistor, and we divide that by the sum so down in the denominator, we have the sum of all the parallel resistors so notice it's 1 over R1 plus 1 over R2 plus all the way for each n resistor. And then that whole thing is multiplied by Is, where Is is the parallel current source. So in this case, we have everything we need. Notice we have a 2 amp source. R1 was 6 ohms. R2 was 3 ohms. R3 was 1 ohm. R4 was 2 ohms. So let's substitute in. Remember, in this case, the thing we're trying to find is current I1. So let's substitute to determine current I1. And if we do that, we determine that I1 must be equal to 1 over Rn. What's our nth resistor here? Well, since we want I1, our nth resistor will be R1, which has a 6 ohm resistance. So in our numerator, we have 1 divided by 6 ohms. And then on our denominator, we have to sum all of those parallel resistors. So we have 1 over 6 ohms from R1 plus 1 over 3 ohms from R2 plus 1 over 1 ohm from R3 plus 1 over 2 ohms from R4. Finally, we must multiply by our current source. Our current source has 2 amps of current. So this might look a little bit ugly at first, right? Like there's a bunch of fractions in here. What I recommend we do is multiply both the numerator and denominator by 6. because basically we're multiplying by 1, right? 6 divided by 6 is 1, so notice what we can do here. Both the numerator and denominator are multiplied by 6. We are left with, up top we have 6 times 1/6, that's just 1. And then on the bottom, 6 times 1/6, that becomes 1. 6 times 1/3, that becomes 2. 6 times 1, that becomes 6. And 6 times 1/2, that becomes 3. Multiply by 2 amps. That gives us 1/12 times 2 amps. We determine, therefore, I1 must be equal to 212 amperes, or 1/6. That wasn't so bad, was it? The important thing was to make sure we used the current division equation correctly and substituted everybody in with the correct units. Let's go ahead and continue on. And once again, if you want to see a cleaner version of the solution, you can see all it is plugging and chugging. Okay, so if you have any other questions on these basic tools, I highly recommend that you reach out and ask some questions. I'm more than happy to help if you have any other questions on this. Let's go ahead and move on to node analysis. So let's start with a basic question. Suppose we have this circuit shown on the right. This circuit is more complex, right? It's probably a little more complex than something you had worked with in physics class or other basic circuits courses. Suppose we wanted to solve for V1 and V2. Question for everybody here is, would our existing methods work for this circuit? Would we be able to combine resistors? Could we combine series and parallel resistors? Looking at this circuit, it's not so straightforward how we would do that, right? We have some resistors that are in series with the current source, but then if you look at it more closely, there's also some strange paths in multiple directions. It's not necessarily straightforward how we could solve this using the tools we already know. Second question, would it be easy to teach a computer to solve this circuit? Not so straightforward, right? The computer wouldn't necessarily be able to easily recognize how to combine resistors and simplify. So long story short, while our existing tools are useful, they cannot solve every circuit. So our existing methods have limitations. So one limitation is that we cannot necessarily analyze all circuits using equivalent resistors and what we know so far. Also, equivalent resistors and current division, voltage division, those are not necessarily easy to automate. So if we wanted to have a computer help us, it'd be kind of hard to teach the computer how to solve our problems. So Key takeaway here: we need a more powerful analysis technique. And so, in fact, the technique we're going to learn today is called node analysis. This is a very powerful technique, and this is actually the technique that we do have computers use in order to solve circuits. So let's talk more about what node analysis is and how we do it. So just giving everybody a preview here. So basically for today's video, we are focusing on node analysis. Some books call it the node voltage method. So we'll cover that today. And in our next video, we will cover mesh analysis, or the mesh current method, or loop analysis, depending on your book. We will see that both of these tools are extremely powerful, and they can be used to analyze those more complex circuits. But first, before we jump headfirst into node analysis, let's review some important tools that we need. Believe it or not, at the end of the day, node analysis is just a special way of applying Kirchoff's laws and the tools we already know. So let's start with a quick review question. We're going to do a few of these questions, so if you'd like, follow along. And feel free to pause the video if you would like to practice on your own before seeing the solution. Okay, so review question 1. Here we are asked to use Kirchoff's current law to write an equation for the currents flowing into and out of node 1. So notice here is our node 1. And we are to use the convention that current flowing into a node is positive, and we also have a grounded voltage of 0 volts down there. We'll return to that grounding a little later. So let's just go ahead and take a look at node 1. We have 4 currents entering or leaving node 1. We have I1 entering. We have IR1 leaving. And then we also have IR2 and IR3 also leaving. So remember, if we apply the bank account convention, that means that since I1 is entering node 1, that gets a positive sign. The other currents that are leaving get negative signs. By Kirchoff's current law, we know that the algebraic sum of all currents entering or leaving a node must be 0. So we can go ahead and take our algebraic sum. We get plus I1, because I1 is entering. The other 3 currents are leaving. So we have minus IR1 minus IR2 minus IR3. And the algebraic sum must be 0. So if you look at our answer choices, let's see what we get. Well, definitely not choice A, definitely not choice B. How about choice C? Yeah, look at that. We've got positive I1, the other 3 are negative. Correct answer here is choice C. Let's try another review question. Once again, feel free to pause the video if you'd like to try it yourself. So here we are told that node 1 has a voltage V1 and node 2 has a voltage V2. We're asked to use Ohm's law to write an equation for IR1, that's this one here, write an equation for IR1 in terms of V1 and the 1 kilo ohm resistor. Okay, well, let's take a closer look at that. So we know from Ohm's law, V is equal to IR. Let's take a closer look at IR1. So I'm going to go ahead and draw a close-up view of this resistor R1. So here we know that we have a resistance of 1 kilo ohm, or 1,000 ohms. Notice I'm proactively converting units to regular ohms so that I don't accidentally make a conversion error later. Notice I'm told that the ground node here is sitting at 0 volts. That means the bottom side of my resistor here is sitting at 0 volts. And okay, I also know that this resistor is connected to node 1. So the top part of my resistor must be sitting at voltage V1 because my resistor is connected to node 1. And node 1 is all sitting at that voltage V1. Okay. So if that's the case, how can I write an equation for my current I1, or in this case, current IR1, in terms of my voltage and resistance? Well, if we apply Ohm's law, we would know that IR1 must be equal to our voltage across the resistor, which is V, divided by our resistance, R. We know our resistance is 1,000 ohms. What's our voltage V here? How many volts do I lose if I walk across my resistor? Wait a minute. Notice this voltage is just equal to V1 minus 0 volts, right? Because initially up here, I'm standing at V1 volts, and if I go across my resistor down to the other side, I will have 0 volts. So in this case, I can write that my current IR1 is just equal to V1 minus 0 volts. So I start at V1, I end at 0 volts. So the voltage drop, or the voltage difference, is V1 minus 0 divided by 1,000. Again, 1,000 ohms is my resistance. Therefore, I can write that IR1 is just equal to V1 divided by 1,000. It's not too bad, right? We're just using Ohm's law here. And you'll see, once again, that's exactly what we get. Our voltage drop across our resistor is V1 volts, so the current must be equal to V1 over 1000. Let's try one more question, kind of similar. Now I'm being asked to repeat the same analysis for IR2 and IR3. So I want to write an equation for IR2 and IR3 in terms of the resistors and voltage V1 and V2. So let's go ahead and consider first our current IR2. Notice IR2 looks something like this. So first I have voltage V1 on the left side, and then I have voltage V2 on the right side. And I'm assuming my current IR2 is flowing from V1 to V2. Another way to think about this is to use our water wheel analogy. Remember, current must be flowing from a higher voltage to a lower voltage. So since we assume IR2 is flowing from V1 to V2, we assume V1 must be greater than V2. So keep that in mind. We might find out after solving everything that V1 is not greater than V2, and if that's the case, we would end up determining that IR2 was negative. But here, let's just keep consistent. Since we are assuming IR2 flows from left to right, let's go ahead and assume that since current flows from positive to negative, our system must look like this. So how much voltage will I lose? Let's just call it V. How much voltage do I lose when I go from V1 to V2? How much voltage drop would I get? Well, notice that I'm starting at a higher voltage V1, I'm ending at a lower voltage V2, right? So in this case, if I go from V1 to V2, my change in voltage, or that voltage V, is just going to be equal to V1 minus V2. That's the voltage that is dissipated by the 2000 ohm resistor. The voltage across that resistor must be equal to the difference between V1 when I entered and V2 when I exited that resistor. So now we can go ahead and substitute into Ohm's law. We know by Ohm's law that IR2 must be equal to the voltage across R2 divided by the resistance of that resistor. So in this case, we're treating that as 2000 ohms. So notice here, VR2, or the voltage across our 2 kilo ohm resistor, well, we know what that is. That's just V1 minus V2. So notice the important thing. Since we drew the arrow going from V1 to V2, we must subtract V2 from V1 because the direction of the arrow assumes V1 is the higher voltage. So you want to make sure that you pay attention to that convention. If IR2 was pointing in the opposite way, we would instead write that IR2 is equal to V2 minus V1 over 2000. Because then we would be assuming that V2 was the higher voltage. So pay attention to the direction. Pay attention to the direction of your arrows and keep consistent. So now let's go ahead and try current IR3. And we'll see that current IR3 is actually the same approach. Once again, we know that resistance that IR3 is flowing through is a 10 kilo ohm resistor, and we're going from V1 to V2. So using the same approach as above, we can determine that IR3 must be equal to our voltage V1 where we started minus V2 where we end up. But this time we have to divide by the resistance that we're passing through, which is 10,000 ohms. But notice the voltage difference is the same, the resistance is different. And there you have it. Notice how helpful it is to draw pictures. Don't be afraid to draw pictures and draw stick figures, use arrows, visualize what's happening. And that can make it a lot easier to solve these questions. And there's our solution. Once again, we see here that our resistor R2 was 2000 ohms and our resistor R3 was 10,000 ohms. And we achieved our expected result. So now that we have done a little bit of practice, let's go ahead and talk through the steps of node analysis. Believe it or not, we actually just did this in our earlier examples. We just did the first steps of node analysis. So basically, in node analysis, all we're trying to do is use the circuit's nodes and Kirchoff's current law to write systems of equations. In particular, we are writing equations in terms of the node voltage and the resistance. And once we have equations for node voltage and resistance, we can solve that system of equations, and it will help us determine all the node voltages in a circuit. And of course, once we know our node voltage, then it's pretty straightforward to find currents and other things using Ohm's law. Here's the general steps of node analysis. First, you want to identify all the nodes. Remember, these are the locations where circuit elements are connected. And remember that the voltage throughout a given node is constant. Once you have found all your nodes, then you need to choose a reference node. We set our reference node to 0 volts, and all the other voltages are found relative to that reference. In step 3, we apply Kirchoff's current law to each node. Remember what we did with the bank account convention? How we summed the currents entering and exiting the node? That's exactly what we do here. We apply Kirchoff's current law to each node in order to get equations in terms of currents. Notice you do not apply Kirchoff's current law to the reference node, because that one's already 0. In step 4, we rewrite the equations in terms of node voltages. We actually just did these 2 steps. So once we have an equation in terms of current, we can use things like Ohm's law to get an equation in terms of voltage. Equations in terms of node voltages are called node equations. You will end up with one node equation for each node. And so at the end of the day, all you need to do is solve the node equations simultaneously in order to find the unknown voltages. So if you have 2 unknown node voltages, you would end up with 2 equations and 2 unknowns. You solve them and you determine the final values of those nodes. This process might sound a little intimidating, but I promise you, if you break it down into individual pieces, it's really not so bad. It's actually kind of fun and satisfying once you figure out how to do it. So please take the time to go through these next examples that we do together. Make sure you really understand this, and reach out if you have questions. Let's go ahead and try a simple example first. Here we are being asked to use Kirchoff's current law to write the node equation for node 1. And we want to write that node equation in terms of node voltages and the resistances elsewhere in the circuit. So basically, what I'll go ahead and do is do the first few steps of node analysis. Remember, first, we need to identify our nodes. Second, we choose a reference node. And then you see, after that, we apply Kirchoff's current law and then rewrite in terms of node voltages. So this is the procedure that we will follow, but we are just going to use this procedure for node 1. Let's go ahead and give it a try. So first we're going to identify our nodes. I'm going to call my leftmost node V1. That's basically this whole area here, right? This whole area, I'm going to assume it is sitting at voltage V1. I have a second node in the middle of my circuit. I'm going to call that V2. And then notice on the right-hand side, this whole area here is sitting at 1 voltage. That is, we'll call it node V3. And finally, I have one more node on the bottom. I'm going to call that V4. So you can call your nodes whatever you want, but you would want to make sure you correctly identify all of them and stay consistent. Our second step is to choose a reference node. So the reference node is going to be set to 0 volts. I want to make as many things as possible 0, so generally you want to choose the node which is connected to the most things. So here, notice V4 is connected to 3 other points. So I'm going to go ahead and make V4 my reference node. Sometimes the reference node will be given, other times you'll need to choose it. So in theory, if you're solving for all the voltages, it won't matter which one you choose, but generally you want to choose one that's connected to lots of things so that you can make lots of things 0. Now it's time to apply Kirchoff's current law. In this case, we only need to apply Kirchoff's current law to node 1 because we are only looking for the node equation of node 1. So here we are just doing node 1. Per the instructions. But of course, if you needed to repeat for other nodes, you would also do a similar process for the rest. So if we take a look at node 1, let's see what's going in and out of node 1. Notice we have a 3 milliamp current entering from the bottom due to that current source. I don't know how the other currents are flowing, but I'm just going to go ahead and start labeling currents. So notice I'm going to let I1 be the current from V1 to V2, and let I2 be the current from V1 to V3. So now we can go ahead and apply Kirchoff's current law. we have 3 milliamps entering. I'm going to change that to 0.003 amps. So notice the 3 milliamps is entering, so it gets a positive sign. Next, I have I1 exiting the node. So I1 is leaving the node, it gets a negative sign. And I2 is also leaving the node. So I2 gets a negative sign. This is my Kirchoff's current law equation. One thing to be careful of is make sure you keep consistent with these arrows. So later on, if I were to need to solve for V3, I would also assume that I have I2 entering V3. I would assume I1 is entering V2. So again, just make sure you keep these currents, keep your arrows in the same direction throughout the problem. Okay, but this is a Kirchhoff's current law equation. That is not my node equation. So our next step, if you remember, is to rewrite my Kirchhoff's current law equation in terms of the node voltages. So let's go ahead and we need to rewrite this in terms of the node voltages. Let's go ahead and do that. So remember we had something like this, right? We had I1 and I2. So we had plus 0.003 amps minus I1 minus I2 equals 0. And we had labeled our voltages as shown. So notice here we need to rewrite I1 and I2 using our node voltages. Let's look at I1 first. We know I1 is flowing from V1 to V2. And so by Ohm's law, we can write that I1 must be equal to whatever the voltage drop across R1 is divided by R1. So we need to find what's that voltage difference. Well, as we discussed, we know that the voltage across resistor R1 is going to be equal to V1 minus V2. It's basically this height difference. So therefore, we determine that I1 must be equal to V1 minus V2 divided by R1. Now let's consider I2. So for I2, notice we begin at node V1 we go through our resistor R2, and then we end up over at V3. So in this case, by the same approach, we can determine that I2 must be equal to the voltage drop across R2 divided by our resistor R2. So in this case, we determine that the number of volts we lose going across R2, well, that's just going to be V1 minus V3. Because remember, we started assuming V1 is the higher voltage and that I2 is flowing from higher V1 to lower V3. Therefore, we determine I2 is equal to V1 minus V3 divided by R2. Here's where the magic happens. We can substitute the I1 and I2 equations into Kirchoff's current law to get the node equation. And if we do that, we get the node equation for node 1 is going to be equal to plus 0.003 amps minus V1 minus V2 over R1 minus V1 minus V3 over R2 equals 0. That is our node equation. If I were to ask you to write a node equation like this on an exam or on a homework assignment, this is what I would be looking for. Notice if we repeated the steps for nodes V2 and V3, you would end up with 3 equations and 3 unknowns, and it would be possible to solve for V1, V2, and V3. You'll do this potentially in a future homework assignment. Once again, depending on how you write your equation, you should end up with something like that. All right, so hopefully now this is starting to make a little bit more sense. Feel free to reach out if you have questions on this. And now let's do a full node analysis example. Remember this circuit from earlier? This was that more complex circuit, and we weren't sure how to solve it using equivalent resistors. But now that we know node analysis, we can actually solve this circuit using the tools that we've learned. So let's go ahead and give this a try. Let's walk through our node analysis step by step. Remember, our first step is to identify all the nodes. How many nodes do we have in this circuit? Pause the video a moment. See if you can count them. You should have ended up with something like this. Notice that just because these points may appear different, these 1, 2, 3, all of these points are sitting at the same voltage. Notice that they're connected by a plain wire or a short. So notice this whole area is a single node, node 1. Similarly, node 2, again, we determine this whole area is all connected by shorts, so node 2 is the portion in the upper right. And finally, we get one more node along the bottom of our circuit. I call that node 3. Our next step is to choose a reference node. And we also call this the ground node. And we assign it a voltage of 0 volts. That way, all the other node voltages are calculated relative to that reference. You can choose any node you want to be your reference node, but here we are specifically trying to solve for V1 and V2. So let's choose the bottom node as our reference. And again, you can also, if you're not sure or if it's not clear which node you should choose, sometimes it will be given to you as a grounded node. Other times you just want to choose the node that has the most things connected to it, so that lots of stuff can be made 0. All right, so our next step is to apply Kirchoff's current law and express our currents in terms of the node voltages. Does this circuit look familiar? Turns out we actually started doing this during our early examples. So let's go ahead and look at each node individually. So we'll look at node 1 and node 2 here, and write node equations for each of those nodes. So node 1 might be familiar because we did this already. So if we look at node 1, we were actually previously looking at the current flowing through those 3 resistors. So we actually kind of started this one earlier. We didn't finish it, but we started it earlier. So we can see node 1 has 10 milliamps entering, so that's plus 0.010 amps. Notice I converted milliamps to amps to avoid potential unit mistakes later. But I need to choose current directions for my other resistors. I'm going to assume, so if currents are not given, remember, if current arrows are not given, you should assume a direction and be consistent. So previously, we had used the currents IR1 for the current going through this portion. We used current IR2 through the 2 kilo ohm resistor, and we used current IR3 for the current going through the 10 kilo ohm resistor. I'm also going to assume IR4, the current exiting node 2 on the bottom, and we have a 50 milliamp source given for the rightmost source. So for node 1, we know we have 10 milliamps going in, or 0.01 amps. We also have minus IR1, because we assume IR1 is leaving node 1. We have minus IR2, so R2 is leaving node 1, and we have minus IR3. This is our Kirchhoff's current law equation. But remember, we need to express each of these currents each current in terms of the node voltages. So in terms of V1, V2, and the resistances. And we did this already in our earlier examples. So you'll remember that we determined that IR1, that's just going to be V1 minus 0 volts divided by 1000 ohms, because we're starting at V1, we end at 0 volts, we pass through 1000 ohms. So by Ohm's law, our voltage V1 is equal to IR1 times 1000. So IR1 will be V1 minus 0 divided by 1000. From before, we also determined that IR2 was simply equal to V1 minus V2 divided by 2000 ohms. And finally, IR3 was equal to V1 minus V2 divided by 10,000 ohms. So therefore, our equation for node 1 that is going to be plus 0.01 amps minus V1 over 1000 minus V1 minus V2 over 2000 minus V1 minus V2 over 10,000 equals 0. Now let's just repeat the same process this time for node 2. Once again, make sure you use the same directions for your current arrows. So in this case, remember we had IR1, we had IR2, IR3, and IR4. So we need to keep those directions the same. We don't want to change them because we are still solving for the same circuit. So if we apply Kirchoff's current law to node 2, to node V2 here, we determine, well, we have IR3 coming in, so that gives us plus IR3. IR2 is coming in, so we get plus IR2. IR4 is leaving, so we give that a negative sign. And then we also have 50 milliamps leaving. So notice here I converted milliamps to amps to avoid unit conversion issues later. Once again, I just need to rewrite IR3, IR2, IR4 in terms of node voltages. So once again, for IR3, we determine IR3 is just V1 minus V2 divided by 10,000. IR2 is V1 minus V2 divided by 2000. We also know that IR4, if this is our ground node, IR4 must be equal to V2 minus 0 divided by 2000. And finally, our 50 milliamp source is already known. So if we substitute back into Kirchoff's current law, we end up with the following node equation. We have plus IR3 then we have plus IR2. So remember, we're now entering node V2. Then we have minus IR4, which is V2 over 2000, minus 0.005, 0.05 amperes equals 0. So notice, we now have two equations and two unknowns. We can solve for V1 and V2. That is the last step of our node analysis. So once again, if you did the node analysis correctly, you should have ended up with equations similar to these. A common mistake is to accidentally mess up your units. Remember, when applying Ohm's law, you need to be working with volts, amps, and ohms. So be careful of milliamps, kiloohms, things like that. Make sure that you use amp and ohm units when calculating. So now all that's left is to solve our systems of equations, and once we've done that, we will actually determine V1 and V2. Remember, these are determined relative to our 0-volt reference node. So don't panic if the voltages are negative here. That simply means that V1 and V2 are sitting at a lower voltage relative to node 3. So just a reminder, use equation solvers to help. One of my favorites is Wolfram Alpha. And you can see in this example, you can just type the equations right in to their system of two equation solver, and you can get the result. Wolfram Alpha can also work well for solving systems of 3 or 4 equations. You just search for however many equations you're trying to solve. All right, so before we move on, we need to also cover a few special cases of node analysis. So there's just a couple special cases, and really thing to remember here is the procedure is the same. There's just a couple minor adjustments you make if you have a special case. First special case is if you have a voltage source between a node and the ground. So if this is our ground for 0 volts, notice in this case, if I'm sitting at 0 volts down below, and then I have a voltage Vs, this node B's voltage, VB, is going to be equal to our source's voltage. Just some free information. So we can proceed with node analysis as normal, knowing that the voltage at node B is equal to Vs. Another special case of node analysis is when we have a voltage source between two nodes. So notice here's one node with a voltage VA, and the second node with a voltage VB. This voltage source is between two nodes. So the thing about Kirchoff's laws is that they're applicable everywhere in the circuit. So what we do is we define a larger node called a supernode. So here we define the whole node containing VA, VB, V1. That whole thing is defined as a supernode. And we just apply Kirchoff's law to this entire area. So in this case, we'd have I1 entering. We could say we have another current leaving. So for the supernode, we could just say plus I1 minus I2 minus I3 equals 0. And we could end up with plus I1 minus VA over R1 minus VB over R2 equals 0. But notice that for the supernode, we also get an extra equation. We can also determine the relationship between the outer voltages. So we can use the supernode to relate the voltages on either side. So if you see a supernode, you should be happy because you get this free information. We have one equation relating I1, VA, VB, and notice from source V1, we can also determine that VA minus V1 is equal to VB. So using these two equations, we can solve for those unknown voltages. Let's do a couple quick examples before we end for today. In this first example, we're looking to find the voltages VA and VB. Go ahead and pause the video if you'd like. See if you can solve these. First thing you can ask yourself is there anything special about that area? Well, this is a supernode. There is a voltage source between two nodes. So, first we want to recognize that there is a supernode. Also, using the supernode, we can determine how the supernode's voltages are related. Got to use that free information, right? So here we determine that VB plus 8 volts, because again we are gaining 8 volts if we walk from VB to VA, VB plus 8 volts must be equal to VA. Because if I walk from VB to VA, I am gaining plus 8 volts. I can also apply Kirchoff's current law to the supernode. So let's just go ahead and assume some currents. So here I'll just let that be my current I1, and I will also assume another current. Let's just call it I2. So here we assume directions for our unknown currents. And so if we apply Kirchoff's current law to that supernode, we determine we have minus I1 plus 3 amps plus I2 equals 0. So now we need to rewrite in terms of the node voltages. Minus I1 is going to be equal to minus VB, let's call this our ground, 0 volts. So we have VB minus 0 over 40 ohms plus 3 amps. And then we have, for this other node, we have basically a minus 12 volt source here because we're sitting at 0 volts on one end of our source. We're 12 volts lower here. So the voltage here is minus 12 volts. So we can see that for current I2, our current I2 is just going to be negative 12 volts minus VA divided by 10, because we're assuming that we're flowing from negative 12 to VA. So here we're going to say plus negative 12 volts minus VA, because we're flowing in the direction of I2, divided by 10. So notice we have two equations and two unknowns. So all that's left is to solve for VA and VB. And if you go ahead and solve for VA and VB, you'll determine that VA will be equal to 16 volts and VB is going to be 8 volts. If I were to ask you a question like this on an exam, I would make sure the math is simple enough that it could be done by hand. On homework questions, you might need to use Wolfram Alpha or an equation solver. And there we have it. One last point to cover about node analysis is node analysis with dependent sources. Once again, if you see a circuit with a dependent source, you should be happy, because it gives you free information. It gives you a hint that you need to relate the dependent source to the node voltages. Otherwise, you do node analysis like normal. Real quick, let's finish up this one last example for everyone. So here, we are being asked to find the voltage VA. Well, we're trying to do node analysis. So let's first apply Kirchoff's current law to node A. If we let the bottom node be the ground, then you can see that node A must have a voltage VA, because notice we're 0 volts down here. We climb up VA volts, so node A must be sitting at VA volts. Let's assume some currents. Remember, it doesn't matter what direction you assume as long as you are consistent. I'm going to go ahead and assume some directions of currents. So I'm going to have I1, I2, and I3. Again, I have no idea whether these are correct. I'm just assuming some currents so that we can write a node equation. And so in this case, notice all of a sudden that our dependent source comes into play. Well, what does our dependent source depend on? Here our dependent source just depends on VA. It's already related to the unknown voltage. So we can just proceed with node analysis as normal. So we just proceed as normal. So here, by Kirchoff's current law, if we apply Kirchoff's current law at node A, we determine that we have plus I1, because I1 is entering, minus I2, because I2 is leaving, plus I3, I3 is entering. Everybody must sum to 0. Now we need to rewrite I1, I2, I3 in terms of our node voltage VA. What do we get? I1 becomes 4VA minus VA divided by 3000. I2 becomes VA divided by 2000, or VA minus 0 volts. VA minus 0 volts divided by the 2000 ohm resistor. And finally, I3 will become, we have 6 volts minus VA divided by 1000. And those three must sum to 0. Now all that's left to do is solve for VA. We got one equation, one unknown. We solve for VA. Here it's convenient to multiply both sides by 6000. So if we multiply both sides by 6000, we end up, and the first two get doubled, so 8 minus 2. Then we have minus 3 VA. Then we have plus 36 minus 6 VA equals 0. And so if we go ahead and do our math here, we will determine 8 minus 2 is 6, minus 3 is 3, minus 6 is negative 3 VA. It's equal to negative 36. So VA is equal to 12 volts. So not so bad, right? At the end of the day, node analysis is simply applying Kirchoff's current law and Ohm's law in order to get equations for voltage. Once you have those equations for voltage, you can either solve by hand or use a solver, depending on how many equations there are. I highly recommend you go back through these examples we did on your own and see if you can get the same result as we did. If you practice a few more of these examples on your own, the process will make a lot more sense and you'll get a lot more confident in your abilities. We're definitely going to use node analysis throughout this course, so I highly recommend you take the time now to master this skill. It will be a big help as we continue on with the class. All right, so that's about it for today. So hopefully now you're starting to get more comfortable applying our existing tools to solve more complex circuits. And now hopefully you see how node analysis can be an incredibly powerful tool to get equations for voltage in even very complex circuits. In the next video, we'll look at another tool called mesh analysis, which can also be extremely powerful. And we'll see that both of these tools are incredibly useful throughout this class. Thanks everyone, and we will see you in the next video.